Question 3. We're given an AC accelerator generator with EMF, electromotive force, amplitude epsilon equals 220 volts, and operating at a frequency of 440 hertz, causes oscillations in a series RLC circuit having resistance of 220 ohms, inductance of 150 millihenries, and a capacitance of 24 microfarads. First, they ask us to find the inductive reactance, which is X sub L. They also ask us to find the capacitive reactance X sub C and the impedance Z. This is actually quite straightforward. The equation is very simple. The inductive impedance equals the inductance times 2 pi times the frequency. We're given the inductance, which is 150 millihenries, and we're given the frequency, which is 440 hertz. So plug and chug. 150 millihenries times 2 pi times 440 hertz. That gives us 414.7 ohms. That is the inductive reactance of this generator. Next, B. Oh, no, not B. Capacitive reactance. The equation, again, straightforward. X sub C equals 1 over 2 pi frequency capacitance. Plug and chug. We have frequency, again, it was 440 hertz, and the capacitance is 24 microfarads. So we substitute 2 pi times 440 hertz times 24 times 10 to the minus 6 because it's microfarads, and we will get 15.1 ohms. Lastly, the impedance. The equation for the impedance is Z, that's the impedance, equals the square root R squared plus the inductive reactance minus the capacitive reactance squared. We just calculated the inductive reactance and we calculated the capacitive reactance. We plug those in, and the resistance is given 220 ohms, 220 squared plus the difference of these two, plug and chug, and 456.2 ohms. That is part A. B, find the current amplitude I, power factor, and the average, we're assuming it's power, the average power delivered to the circuit. Now, first, the current amplitude is given simply by the equation I equals E over the impedance. Kind of looks like I equals V over R. Very similar. We have E, that's given, 220 volts, and the impedance we just calculated from part A, we plug in here, 456.2 ohms, we'll get 0.482 amps. Second, we're asked the power factor. Now the power factor is simply cosine of phi, which is equals resistance over impedance. Resistance again is given 220 ohms divided by the impedance, 456.2 ohms. We'll get 0.482 with no units. Again, this is ohms divided by ohms. So we will have a unitless answer. Last, they ask us for the average power delivered to the circuit. So the average power is quite simple equation. This is all in the textbook. Power equals 1/2 voltage times the current times the cosine of the angle between the two phasors, which I will explain in part C. Plug and chug. 1/2 voltage is given, which is the epsilon, so it's 220 volts, times the current, which we calculated up here in the first part of B, 0.482 amps, and that's squared. No, times the cosine, times the cosine of phi, which is this. That gives us 25.6 watts. C. As I mentioned before, this is where you will understand what cosine of phi is and what phi is. So we draw a phasor diagram, as it says here, draw a phasor diagram, including the phasors for the current, the voltage across the resistor, the inductor, and the capacitor. All voltages, voltage across the resistor, voltage across the inductor, and the voltage drop across the capacitor. So that looks like this diagram. So this is what the phasor diagram looks like. Now, phi is the angle between the current phasor and the voltage phasor. That is phi. That is what we calculated over here, phi. Cosine phi is the power factor. That is C, so you can see the phasor diagram. D. What is the resonant frequency of the circuit? Well, when we have resonant frequency, the impedance will equal the resistance. In order for the impedance to equal the resistance, we will have a situation, and let me write here, Z squared will equal R squared. But in order to have this, the X sub L, which is the inductive reactance, must equal the capacitive reactance so that this equals 0. And if this difference equals 0, then the impedance will equal the resistance. So the inductive reactance and the capacitive reactance are equal. The inductive reactance, as you can recall, is L 2 pi F, which is here, and the conductive reactance is 1 over 2 pi FC, which is here. Now from here, we solve for F. So we're going to divide both sides by L 2 pi, and we're going to multiply both sides by F. So we should get F squared, 1 divided by 1 over, let me put L, C, we have 2 pi, divide both sides by 2 pi, so we'll have 2 pi squared. Now to solve for F, get the square root, which will give us 1 over, square root of 1 is 1, square root of LC times 2 pi. And this is what we have here. So in order to get the resonant frequency, we solve for F, and F gives us 1 over 2 pi square root of L divided by C. We plug in, we plug in L, which is 150 millihenries. We plug in capacitance, which is 24 microfarads, and we get 83.88 hertz. That is the resonant frequency. Lastly, at the resonant frequency, what is the average power delivered to the circuit? Well, remember, at that frequency, Z equals R. So we can replace, this will look like I, current equals epsilon divided by R, which is what we have here. We plug in, E again is 250 volts, 220 volts, divided by the resistance, which is 220 ohms. That gives us 1 amp. So at this frequency, the current is 1 amp. They ask us for the average power. We have the average power equation here. So we can just use that again. P average equals 1/2. VI, we have plug and chug equals 1/2, 220. The current is 1 times 1, and we get 110 watts. Our answer for E is 110 watts.